This is the Smart Material Energy Harvesting Kit version 1.3, the tutorial. The first thing we're going to look at, of course, is the outline for the Smart Material Energy Harvesting Kit tutorial. We're going to briefly introduce energy harvesting under what is energy harvesting, and having established that, we're going to look at what is the energy harvesting kit, and energy harvesting is here abbreviated to EH. We're going to look at its components, and then using those components, how to set up the EH kit. Next, we're going to look at the operating values, and then we're going to go to the experiments. We're going to look at how to measure input impedance, accumulated energy, self-storage capacitors, and lastly the CL50. What is energy harvesting? Briefly put, energy harvesting is the process by which energy is extracted from external sources, such as solar power, thermal energy, wind energy, water power, and kinetic energy. We've all seen solar panels that create energy harvested from the sun, or wind turbines used outside of large cities or places to generate electricity. Water power is also a way we harvest energy. Think of the Niagara Falls and back in the day when Nikola Tesla first created electricity using the waterfall's power. We've been harvesting energy for ages in many ways and are always looking for better, more eco-friendly ways to harvest energy and lower our costs. The energy harvesting kit falls under kinetic energy harvesting. This is the energy harvested from vibration. The EH kit in particular studies kinetic energy harvesting with the MFC. Now on to the EH kit in particular. What is the EH kit? Well, it is a prototype and development tool for studying and researching kinetic energy harvesting with the MFC. Piezoelectric harvesters provide complete battery-free devices. Complete electronic devices with a power consumption of less than 10 milliwatts second can be manufactured cost-efficiently. The EH kit is also an educational tool used by researchers and universities to demonstrate applications. On to the components of the EH kit. Let's look at those. You should have all of these included. You will have an amplifier module which you will use to power the shaker. You will have 3 MFCs included, 2 of them already bonded with a cantilever. There is the shaker with a controller. The shaker is used to shake your cantilever and provide motion for the MFC to utilize. You will have a power plug with an adapter included, a conditioner, and 4 modules. The first module is for plain and simple energy harvesting to measure input impedance. The second will be for measuring energy output, and the third is an LED module to see cool colors and basically, measure the LED lights output of energy. The fourth one is the CL50 module, and that's an important one because it's used to power electronics, and you'll find that one in a black conductive bag. Note that all of the modules are labeled except for the LED module, which is unlabeled but pretty straightforward with 3 LEDs, and then the CL50 in the black conductive bag. Last, don't forget your oscilloscope or a multimeter to study your energy output. The most important component in the EH kit is the MFC, the macrofiber composite. It is so important because it is the active element harvesting the energy from vibration. The macrofiber composite actuator is a high-performance piezoelectric fiber composite strain device. It is made of rectangular-shaped piezoelectric fibers put in between adhesive and electrode polyamide film. The macrofiber composite was developed at NASA Langley Research Center during the late 1990s and patented in 2000. The macrofiber composite is a reliable 10 to the 9th cycles as an actuator and also for more than 10 to the 10th cycles for energy harvesting. The MFC is also broadband. It allows for easy non-resonant and resonant energy harvesting applications integration of electronic components. In your EH kit, you will find one piece of the MFC 8528P2, which is already attached to the cantilever. You will find 2 pieces of the MFC 2814P2, one attached to the cantilever and another one on the side for further use. The second component you should look at is the shaker. The shaker is used to generate kinetic energy by moving the MFC cantilevers up and down using variable frequencies that you control. The shaker is powered by the amplifier module. As you can see on the picture, you will mount the MFC on the cantilever onto the rod of the shaker. There is also a controller cable included, which you will unwind to plug into the amplifier and power up the shaker. This leads us to the amplifier module. This generates the control output voltage for the shaker. As the photos show, you have an option to control amplitude and frequency using the amplifier. Frequency can be selected as low as 5 Hz and as high as 60 Hz by increments of 1 Hz by pressing the frequency minus and frequency plus button to increase and decrease value. This controls how frequently your cantilever is moved up and down. The amplitude or power will be set with A- or A+, and at level 0 the output is disabled. Amplitude here measured by levels. The corresponding mechanical strain is the result of mechanic load and power selection. Now that we have a general idea of our modules and how to use them, let us go and use the kit. First of all, open the box, take out the shaker and make sure to absolutely not pull by the rod, because this might damage the rod and or the shaker. Find yourself a screwdriver, as you will have to take off the 2 screws on the shaker rod, release the screws and use the screws and your screwdriver to attach the cantilever back onto the rod. The harvesting modules included in the kit are pictured and briefly described here by me. You have the variable impedance module, the VIM, which is used to measure energy output. Then you have the energy measurement circuitry, used to measure harvested energy over time. Third, you have the LED board, which is used for demonstration. And then the CL50 or the Smart Module 1.3, which is used to power electronics. After you've mounted the cantilever with the MFC onto the shaker, pick your module for measurement. After you have picked your harvesting module, plug the MFC's red and black cable to the module's MFC in, which is located on the back of the module without preferred polarity. Note that the application power supply should be connected to V+ and GND. Next, plug the shaker's controller cable into the amplifier's audio out plug. Then, connect the power plug into the 12V in the back of the amplifier module. Connect the modules out to an oscilloscope or a multimeter. On the amplifier, turn to internal. It should show in\X on the screen next to where it says frequency. The module will switch between internal and external frequency source by pressing internal\external. For all your experiments, you can increase frequency or decrease frequency and raise and lower amplitude. Next, connect the oscilloscope to the back of the module under Module Out and turn on your oscilloscope. It's going to start graphing, and note everything there and then make a graph yourself, frequency versus amplitude. I used an Excel spreadsheet in my case, graph your results. Some tips here are, you can fix a piece of mass between 20 grams and 50 grams at the end of the beam to get higher amplitude. I used a pen in my case in my experiment, and I placed it at the tip of the cantilever. Also, the integrated amplifier can be powered from external source via BNC connector. Before we start our first experiment, let us look at the operating values. We have electrical, temperature, and mechanical stress. First, we're going to look at electrical. The input voltage for your kit is at 12V, the input current at 1 amp. For the smart module, make sure that you do not exceed 10V for the input voltage. Second, we're going to look at temperature. Your storing temperature for the kit is at -10 centigrade to +80 centigrade. You may operate it or use it at +5 centigrade to +30 centigrade. Third, we're going to look at mechanical stress. The maximum strain for the MFC is 500 parts per million. Now on to our first experiment, measuring input impedance. First of all, take your harvesting module, the variable impedance module, the VIM, and connect it to the MFC. Then, connect the output of the VIM to an oscilloscope or a multimeter. Now you're ready to graph. Measure the peak-to-peak effective value output voltage measurement of the VIM for various resistor values and note your results in a chart, which you can call up on Excel. This serves to simplify the evaluation. Take a look at the chart on the right as an example. At some frequencies the amplitude of the beam is low. You can fix a piece of mass between 20 grams and 50 grams at the end of the beam to get higher amplitude, as I've already said. Also, repeat this experiment with different frequencies, different amplifier levels, and different MFC types to get to know the behavior of the MFC. The MFC acts as an energy source with an internal resistor. Take a look at the cool picture on the right to simplify what I'm saying. It is described by input resistance and idle voltage. The parameters of those can be evaluated with a simple external resistor or the resistor load and a voltage measurement unit. For each adjusted resistor value, one corresponding peak-to-peak voltage is measured, as the graphs below will show. Note the difference between adjusted resistor value and external resistor used depending on the MFC type. In our next step, convert the peak-to-peak voltage into effective voltage. I have provided you the equation for this here in step 4. Next, in step 5, calculate the electric power provided from the MFC. Use here the effective voltage value you received from your step 4 equation to measure this. P stands for power and R for resistance. Take a look at the graphs. The maximum power point changes when you change the frequency. At the MPP, the maximum power point, the external resistor equals the internal resistor, or R2 equals R1, so the value of the internal resistor depends on the frequency. For very low frequencies, do attach a mass on the tip of the MFC to perform symmetric bending. Our next experiment is going to be about accumulating energy. First, choose the energy measurement circuitry, which is the second module I talked about earlier. Connect the MFC to this module. It helps to have the VIM disconnected, otherwise you might run into problems here. Choose your capacitor. These are all located on your circuitry. We have the external custom capacitor, a 0.1 farad gold cap, a 22 microfarad tantal cap, and the 470 microfarad electrolyte cap. Did you choose your capacitor? Alright, next step. Connect the output of the module to an oscilloscope or a multimeter if you're using the gold cap at DC out. Discharge and charge the capacitor by pressing the round black button and then start the amplifier. A few notes I took down here when I did this experiment. If you turn off the capacitors, you will see the original signal. Also, switching polarity will cause the energy measurement to decrease. The value of the capacitor and voltage is equal to measurement of produced energy. For visual acuity, I have included here a chart with the different capacitors that you will use to accumulate energy. I have also made you a chart of useful measuring time intervals for different capacitors. Notice that the time interval for the gold cap takes much longer to charge at 30 seconds than the tantalum cap at half a second or the electrolyte cap at 5 seconds. Be aware that for the capacitors, the voltage should not exceed maximum capacitor voltage levels, which are only series for the 0.1 farad gold cap with 5 volt. The maximum capacitor voltage of the small tantalum cap is reached very fast after only a second, so just release the discharge button for 1 second to measure the curve, and then press it again. After vibration of the MFC, the energy is temporarily stored in the module until it reaches a certain level. The output of the module is enabled and 3.3 volt is supplied for the time that the energy is converted. Note here the equation you can use to calculate stored energy after a defined acquiring period. The W stands for watts, C for the type of cap, and V for voltage. T, of course, is time. The on time is dependent on user application's current consumption. Let us move on to the next step, but please first discharge your capacitor. Our third experiment is on the self-discharge of storage capacitors. After measuring the different capacitors in the last experiment, note that each capacitor principal has a leakage current which needs to be understood by the user when designing a storage system for particular user application. Use the energy measurement circuitry for this experiment again. Of course, disconnect the VIM if you've been using it. Choose your capacitor once more. The best is 22 microfarads for this experiment, so the tantalum cap. Of course, you can also use the external custom capacitor, the 0.1 farad gold cap or the 470 microfarad electrolyte cap. Did you choose your capacitor? Great. Now you connect the output of the energy measurement circuitry to the oscilloscope. The multimeter here is only good for the gold cap. Then, charge your capacitor, whichever one you're using, to 5 volt. For the gold cap, charge it to 2 volt. Charge your capacitor by using the power amplifier or simply tipping the MFC. Make sure your voltage measurement equipment has a high input impedance, higher than or equal to 10 mega ohms. Then stop loading and measure the voltage in time. Use the intervals 1 second, 10 seconds, and so on for your graphing. Here are some useful time intervals in case you are using the bigger capacitors. Notice that the gold cap has a discharging time of a day, while the discharging time for the tantalum cap is only 10 seconds. The electrolyte cap in comparison isn't too bad at 300 seconds. You can calculate the discharge resistor by the formula I've supplied here. You can draw the voltage to time curve to see the exponential discharging behavior of capacitance. On to our next experiment using our LED board module. This module can be used to light up 3 LEDs with the harvested energy based on frequency and amplitude. This is a really straightforward and visual experiment. Connect the LED board to the MFC in and turn on the amplifier. The red, then the yellow, and eventually a white LED on the board will turn on based on the frequency and amplitude you're using. The red light in my experiment turned on at about 17 Hz. Experiment with different frequency and amplitudes to see when the light or the lights turn on. The last experiment we'll do for this tutorial is the Smart Module 1.3, or also called the CL50. The energy from this module can be collected and provided to power electronics. It acts as an interface between the high impedance source characteristic of the MFC and the user application. In most cases, this is microcontroller based. In our first step, choose the Energy Harvesting Module 1.3 out of the black conductive bag. Take a look at the photo to the left showing you the Energy Harvesting Module for reference. You might also notice the spelling of module without the E. This is because the original instruction was written by a German physicist, and here the German spelling of module is used. Plug the MFC to MFC in without preferred polarity and then start the amplifier module. After vibration of the MFC, the energy is temporarily stored in the module until it reaches a certain level. After that, the output of the module is enabled and 3.3 volt are supplied for the time that the energy is converted. The on time is dependent on the current user's consumption. Use the formula I've provided here for on time. Next, disable the output voltage. When the enable pin is pulled to active low, all the stored energy is transferred to the output until the internal storage is empty. The module will start collecting energy from the MFC when the enable pin is high. Please note that this might take some time depending on the energy delivery of the MFC until the 3.3 volt output is available. Take a look at the specifications below. Having done this experiment, ask yourself, which effectiveness does the CL50 module show in providing electrical energy for a certain application, which consumes only 3.3 volt at variously selected kilo ohms? List your theoretical and practical comparisons as they arise while you do this experiment. As with the previous experiments, you can map your results with time, voltage, and energy. Good luck with the experiments, and thank you for choosing and watching the Energy Harvesting Kit Tutorial 1.3 by Smart Material. If you have any questions or concerns or comments or just plain feedback, don't hesitate to contact us. Our email is info@smart-material.com. Our Facebook page name is Smart Material USA. You can also, of course, contact us through our website, smart-material.com. Happy experimenting!